So if you recall at the end of last week, the last video I left you with was looking at the divisibility rules and then saying that we now have the ability to prove why those divisibility rules are the way that they are. So let's take a look at a proof for 9. So remember, the divisibility rule for 9 says that a number is divisible by 9 if and only if the sum of its digits is divisible by 9. Now, the first thing that we want to think about is that if we're working with congruences, what does it mean to be divisible by 9 in regards to congruences? Well, if we're thinking that a number is divisible by 9, that means that's going to be congruent to 0 mod 9, right? Because we're talking about remainders, so if a number is divisible by 9, the remainder is 0, so it's going to be congruent to 0 mod 9. So that is what we're basically trying to prove, is that we're going to try to prove that a number is congruent to 0 mod 9 if and only if the sum of its digits is congruent to 0 mod 9. Alright, so let's take a look at how we're going to structure this proof. Is that we need to start with just an arbitrary number. Now, if we think about numbers, for instance, let's say we have 4637. Okay, so we have 4,637. We're going to try to use some properties that you probably learned maybe in 4th or 5th grade that you never thought that you would ever need. But it's a really good idea to understand how these numbers work, is that this number can be seen as taking 7 plus 30 plus 600 plus 4,000. Right, so we could write this number as each of these numbers represented in its powers of 10 place, basically. So we could rewrite this as 7 plus 3 times 10 plus 6 times 10 squared plus 4 times 10 cubed. So our number system is a base 10 number system, meaning that each of these spots that we write a number, that corresponds to some power of 10. So we're going to use this fact here that we can write numbers like this to be able to approach an arbitrary number and see how do these individual digits relate to the total sum of the number. So we're going to start with an arbitrary number. So I'm going to call this n. This is going to be, say, a sub 1, a sub 2, a sub n. And I'm going to use this notation. Actually, we're going to use, let K be this. I'm going to use this notation to mean that I'm not multiplying these together. In this example, this would be, say, a sub 1, this would be a sub 2, this would be a sub 3, and this would be a sub 4. So I'm writing it in just this form to indicate this is just one number just put together where each of these represents the digits within there. And I don't know how long of a number it is. I'm just going to say that this is just an arbitrary n. Now, what we have is this number. We see that also k, if we think about what we've done in this situation, if we think about this process of how we rewrote 4,637 using these powers of 10, I'm going to do the same thing over here. So k, I'm going to start with this last one. This is going to be a sub n. Then the next one is going to be a sub n minus 1 times 10. We can say to the first if you want. This would be 10 to the 0. We have plus a sub n minus 2 times 10 squared plus a sub n minus 3 times 10 cubed. Now notice there's going to be a pattern that's going to be forming here of how do we come up with the power with the subscript? How do those match up? Well, notice here I have n as my subscript, power of 10 is 0, those add to n. Subscript is n minus 1, that is 1, they add to n. So I can keep going until I reach, say, a sub 2, and this is going to be times 10 to the n minus 2, plus a sub 1 times 10 to the n minus 1. So this is how we can write our number now using powers of 10. Now, we need to try to work with things mod 9. Now, if you recall last week, I said that one of the tricks that we can do when we compute modular arithmetic is we can reduce things mod n before we start doing calculations, right? So we looked at an example. So if I said, say, 3 times 7 is congruent to, say, x mod 2, I could reduce these mod 2 before I multiply them. So this would be 1 times 1 is congruent to 1 mod 2. So I can reduce these, and then I multiply these together to get my mod. Now I could also reduce that if I needed to, but in this case I don't need to anymore. So we're going to use that same trick here. I'm going to take each of these numbers, and I'm going to look at this mod 9. So to see this modulo 9, we have k is going to be congruent to a sub n plus a sub n minus 1 times 10 to the first plus a whole bunch of other things plus a sub 1 times 10 to the n minus 1 mod 9. Okay, so I have this statement, right? So we're just going to look at this mod 9 and see what happens. So then I'm going to reduce each of these mod 9. So this implies that k is congruent to a sub n mod 9 plus a sub n minus 1 times 10 mod 9 plus a whole bunch of these plus a sub 1 times 10 to the n minus 1 mod 9. Okay, so I have these, and then I know what happens with each of these, right? So 10 mod 9, well, that's going to be congruent to 1 mod 9, right? Same thing for any power of 10, right? So if 10 is congruent to 1 mod 9, if I square that, 10 squared, well, then I'm reducing 10 first mod 9, so that's 1. 1 squared is 1. Right? If I reduce 10 cubed mod 9, I can change this to 1 cubed mod 9, which is just 1. So notice all of these become 1s. So this is now congruent to a sub n mod 9 plus a sub n minus 1 times 1 mod 9 plus all of these plus a sub 1 times 1 to the n minus 1 mod 9, which is, if I combine all of these, so 1 to any power is going to be 1, I'm going to add all of these and I'm going to pull the mod back out. So I'm going to have a sub n plus a sub n minus 1 plus a sub 1 mod 9. So I have this statement here. So k is congruent to a sub n plus a sub n minus 1 plus all of these down to a sub 1 mod 9. So what we have now shown is that the remainder of k when we divide it by 9 is the same as the remainder when we add up all of the individual digits from our number. And that's exactly what we wanted to prove. So therefore, we see that k is congruent to 0 mod 9, which what this implies is we're saying that k is divisible by 9 if and only if the sum of the digits is congruent to 0 modulo 9. Or in other words, we're saying this is divisible by 9. So this is exactly what we wanted to show. K is divisible by 9 if and only if the sum of the digits is divisible by 9. And so this is how the rule works for divisibility. Now notice this is also pretty cool because if you're trying to figure out in general what is any remainder when you divide by 9, well, you just look at the sum of the digits, right? So if you think about any number, so let's say we look at, say, 73, right? If you divide that by 9, what's the remainder? Well, you could add these digits together and you get 10, and this is going to be congruent to 1 mod 9. So you know the remainder of 73 when you divide it by 9 is 1 because the sum of the digits is congruent to 1 mod 9. So you not only get this fact about divisibility, you also just get the general thing that holds for all of the remainders. So this is what it looks like mod 9. So if you think about how you could adapt this to other numbers, well, the key is this step over here, right? Once we write it into this form, if I wanted to look at this, say, mod 11, right? I could change this to mod 11. I could change all these mod 11, and I'm looking then again, what's happening to 10 and 10 to any power mod 11? And so similar to what we did with 9, we saw 10 to any power gets reduced to 1. Well, 11, on the other hand, that's going to be reduced to plus or minus 1, right? Like 10 is going to be congruent to negative 1 mod 11, but 10 squared, that would be negative 1 squared, that's going to be 1. So 100, which is 10 squared, that's going to be congruent to 1 mod 11. So that's why the divisibility rule for 11, so that we add and subtract alternating numbers, because that's what's happening to 10, powers of 10, when you look at that mod 9. And so you could take a look at this for any of these rules, but mod 9, I think, is one of the coolest cases to look at. And so I'm going to have one short video after this for those who plan on teaching in particular. That could be a really cool thing that you can teach your kids how to check their answers.